In the settler, it is necessary to avoid at all times certain flow paths that cause hydraulic short circuits or dead zones caused by differences in water temperature or wind-driven circulation patterns. For example, figure A shows the desired flow pattern in the settler to flow homogeneously. This is achieved by placing a distribution device, such as a baffle screen, which causes piston flow, favoring settling of the flock formed. It can also present a stratification due to differences in water density according to figure B. If the incoming water is colder than the water in the settler, it will form a current at the bottom, since the cold water is denser and tends to flow from below, lifting all the settled sludge and causing operating problems. The opposite may occur according to figure C, where the incoming water is warmer than the water in the settler. In this case, it will be lighter, and the flow will tend to go through the upper part of the tank, leaving the rest of the space unused. The flock will not have time to settle. It will be dragged towards the next piece of equipment, which is the filtration system. In the same way, what is presented in figure D can occur, which, due to the action of the winds, forms circular currents on the surface that cause the failure of the settling tank. To avoid this type of flow problem, devices are usually placed to distribute the water correctly inside the settler. One of the most commonly used methods is the overflow, in which there is a diffuser wall with holes that is placed at the inlet of the tank. This is a wall with many holes strategically placed to redistribute the water flow evenly. The orifices should be 100 to 200 millimeters in diameter or equivalent size and should be evenly distributed on the wall. The flow velocity through the orifices should not exceed 0.15 to 0.2 meters per second. Another way to distribute the water homogeneously is by the bottom outlet method, where there is a flow baffle set at the middle or mid-depth of the settler so that the incoming flow hits this horizontal partition and distributes the water in the tank. There is also the option of combining the submerged orifice and the flow baffle so that the water is introduced more or less through the center of the settler and distributed horizontally. Finally, there is the combination of a submerged orifice and a diffuser wall. Any of these techniques allows the flow to be properly distributed and avoids problems with flock settling. This illustration shows a settler and the perforated diffuser wall, which is one of the most practical and effective methods for achieving homogeneous and horizontal flow distribution, with orifices of 100 to 200 millimeters in diameter. It also has the same rectangular settlers with a slight variation at the bottom. In the sludge collection area, there is a cone-shaped slope to facilitate the collection of the sediment and, in this way, improve the extraction when purging, as seen in the front view of the figure. The discharge of water from the settler should be as uniform as possible, and weirs such as the crested weir or the submerged orifice weir are used for this purpose. The notched weir is the most commonly used because it is easy to construct and produces an effluent with good uniformity. The water overflows through the collection channel and is conveyed to the seepage. The figures show serrated weirs that carry the water homogeneously. An empty rectangular settler is shown below. At the bottom, the perforated wall can be seen for the proper distribution of the flow, and also the water collection troughs with serrated weirs, which will uniform the collection of water to the filter. The sludge zone must be collected and discharged in a timely manner. Otherwise, it may affect particle settling. Sludge can be collected and discharged in many ways. The figure indicates that the settler has a collection hopper and, through a pipe reaching to the bottom, can discharge by hydrostatic pressure. Depending on the model of the settler, it may have one hopper in the inlet area or several hoppers along its length, which will not require sludge scraping, but will have their own discharge piping. If the sludge zone has only one collection hopper, it is necessary to supplement it with mechanical sludge scraping equipment. Consequently, there will be equipment with chain and flight scraper and also a traveling bridge. The novelty of this scraper lies in the fact that the scrapers during the lower stroke drag the sludge towards the collection hopper, while during the upper stroke they drag the floating substances towards a lateral trough. The chain scraper is essentially composed of a control-geared motor, a drive shaft provided with two wheels at the ends, and two drag chains. There could also be a chain scraper that only cleans the bottom. The second piece of equipment is the traveling bridge scraper, which travels back and forth along a guide rail to drive the haulage blade. As the vehicle approaches the hopper, the blade drops and pushes the slurry into the hopper. When the vehicle moves away from the hopper, the blade lifts, and the cycle repeats. A third suction pumping mechanism can be used. It consists of a traveling bridge and a pipe with a suction nozzle that reaches to the bottom but does not touch it, so that by suction, the sludge is drawn upward through the pipe and discharged. It will also slide back and forth. When using mechanical sweeping units, the speed of the sweeper should be kept below 18 meters per hour to prevent the deposited sludge from being resuspended. In the case of suction sludge removal units, the speed may be 60 meters per hour, since the main objective is not that the deposited sludge is resuspended, but that the settling process is not disturbed. In the different types of horizontal flow units, sludge or sediment removal can be done intermittently or continuously. The intermittent sludge removal system is used in small installations or when treating relatively clear water. For this purpose, it performs the bottom purges and every 6 months empties and cleans thanks to pressurized water hoses, since usually the sediments are compacted and transformed into a pasty mass that slips very difficult. For continuous sludge removal, the mechanical systems mentioned above are used. The fundamental design criteria for horizontal flow rectangular settlers that must be considered are presented, as is a table with parameters such as surface loading rate, effective water depth, retention time, horizontal flow velocity, and minimum longitudinal to width ratio. There is another table of design-relevant parameters according to other authors for those who are designers